G'day guys, in today's video we'll be talking about induction inequalities. We have two examples here. So the first example says prove z to the power of n is greater than n cubed for all integers n greater than or equal to 10. Second example is prove n squared is greater than or equal to 2n plus 1 for all positive integers n greater than or equal to 3. So start with the first example. Let's do it over here. EG1 says prove 2 to the power of n is greater than or equal to n cubed. First step, same three steps we've got to follow. So step number 1, is let n equal to 10 in this case. So 2 to the power of 10 equals to 1024, and the 10 cubed in this case is 1,000. So therefore 2 to the power of 10 is greater than 10 to the 10 cubed in this case. True for n equals to 10. True for n equals to 10. Step 2. Assume n equals to k. K in this case, so this will then become 2 to the power of k is greater than k cubed in this case. And then now prove n equals to k plus 1. Same thing, 2 to the k plus 1 is greater than k plus 1 all cubed. To solve this, looking back at the previous video that we'd covered, every time we have x greater than y, the best way to solve those is going 2 to the k plus 1 minus k plus 1 all cubed is greater than 0. So LHS minus RHS equals to 0 in this case. We equate this, so I'll just equate the left-hand side in this case. HS is then 2 multiplied by 2 to the k minus k plus 1 all cubed. So pull out the Pascal's triangle, you've got 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. This will be k cubed plus 3k squared is 1, 3, 3. Yeah, plus 3k plus 1 in this case. But coming back to this hypothesis that we created, 2 to the power of k is greater than k cubed in this case. So how can we replace this over here? We can then just say, if it's greater than that, we can obviously substitute then k cubed to 2 to the k, because obviously this is greater, so if something's greater, we can always bring something like lower than that. So we can then have 2k cubed minus k cubed minus 3k squared minus 3k minus 1 in this case. Or is it, did I make a mistake? Because 2k and then, no, let's just do this. So let's scrap this part here. Let's scrap that part. We'll just rewrite this over here. So 2 k cubed minus, let's not open the brackets. Let's keep it as that. K cubed plus 3k squared plus 3k plus 1 in this case. Correct? This then becomes k cubed minus, we have 3k squared in this case plus 3k plus 1, as that then gives me, that will then be greater This is LHS. So k cubed minus 3k squared plus 3k plus 1. Next step would be k cubed minus 3k squared plus 3k squared plus 3k squared, since we write this since k is greater than 1. Correct? Next step would be k cubed minus 9k squared. Factor out the k. We then get k squared brackets k minus 1, k minus 9 in this case. But we know that that is going to be greater than 0, since k is greater than or equal to 10. So, therefore, step 3, by mathematical induction, true for n equals to k plus 1, and true if n equals to k, n equals to 10, hence true for n greater than or equal to 10. So that is how you do example 1. Now we'll get on to example 2. Looking at this next example, step 1, I will do is let S of n be the statement this, so we get n squared minus brackets 2n plus 1 is greater than 0. Correct? So step 1, let n equal to 3, because it's n greater than or equal to 3 for all positive integers. S of 3 gives me, we have 3 squared minus 2 times 3 is 6 plus 1 is 7, greater than 0. So 9 minus 2 is 2 is greater than 0. Therefore, true for n equals to 3. So it's true for n equals to 3. Let's go to step 2. Step 2 is assume n equals to k in this case. So S of k then gives me S of k gives me k cubed, k squared, sorry, my bad, k squared minus 2k plus 1 is greater than 0 in this case. So we can rewrite that as k squared minus 2k minus 1 is greater than 0. Proof for n equals to k plus 1. K plus 1, so we then get S of k plus 1 is going to be k plus 1 all squared minus 2k plus 1 minus 1 is greater than 0. LHS, let's just try and simplify the left-hand side. So we have k plus 1 all squared is k squared plus 2k plus 1 minus 2k minus 2 minus 1 is greater than 0. Rewrite this as k squared minus 2k minus 1. Correct? Plus 2k minus 1 in this case. But we know k squared minus 2k minus 1 from step 2 assumption is that that is greater than 0. So we can change this to 0 plus 2k minus 1. But we know that, I'll bring this over here. So 0 less than 0 plus 2k minus 1. But we know that 2k minus 1 is greater than 5 because n is greater than or equal to 3. So 3 times 2 is 6 minus 1 has to be 5. Correct? Oh, it to be greater than or equal to 5. So, if that's the case, then hence, it is proven that for n plus 1, it has to be greater than 0. So hence, s of, sorry, that won't be equals to, that will just be greater than 5. Because we already have an equals to here, greater than or equal to here. So hence, s of k plus 1 is true if s of k is true. Therefore, step 3, by mathematical induction, it's true for n greater than or equal to 3. So that is how you do these two examples in induction of inequalities.